everyone. Let us start lecture 6. And the topic, since we have already covered little bit of background on the basis of which mixed potential theory has been has evolved. So, now we will gradually move into discussing corrosion events on the basis of mixed potential theory. So, the topic would be explaining corrosion processes, I would say, on the basis of mixed potential theory. So, when we talked about mixed potential theory, we said that it is based on two hypotheses. One is any electrochemical process can be divided into a number of simple cathodic or anodic processes. So, it consists of number of cathodic and anodic reaction, and there could be situation that one particular reaction, one particular electrochemical process, let us say zinc dissolution in acid, it can have a situation like there could be one cathodic reaction, one anodic reaction, there could be situation like multiple numbers of cathodic reaction and one single anodic process, cathodic reactions and one single anodic process. So, we will see those situations one by one, and then the second part is there should be charge balance. Charge, I would say charge conservation. And it also leads to a mixed potential which is lying in between the equilibrium potentials of those cathodic as well as anodic reactions, and at that potential we have a situation which is called IC equal to IA, and this summation sign means that it consider all the cathodic reactions, that current density corresponding to that, and IA corresponds to the all the anodic processes, anodic reactions. So, this is the mixed potential which we call it E mix, and later we will see that this is nothing but E corrosion. So, on this two hypotheses this mixed potential theory is built on, and while we discuss this, we will see that we need to understand, we need to make use of our understanding of polarization, and we have already seen these two polarizations. One is concentration, one is concentration polarization, another one is activation polarization. Initially, we will see processes based on activation polarization, and we will also consider some processes, corrosion processes, where concentration polarization is used up. Is used to understand that particular process. Now, as we see that the first hypothesis, there could be a number of situations. Situation 1, let us say situation 1, there could be one cathodic plus 1 anodic. Then situation 2, two cathodic plus 1 anodic reaction. Situation 3, there could be 3 cathodic reaction plus 1 anodic reaction. This is one set. So, that means we can have multiple cathodic and one unique anodic reaction. There could be a situation like 4 where we can have 1 cathodic plus 2 anodic reactions. Fine. So, this is another situation. Now, while we consider these 4 situations, we are going to assume that anode and cathode both have same area. But when we can have one more situation where anodic and cathodic area could be different. That means, this is one unique situation. And what do we mean by anodic and cathodic area? The area over which cathodic reactions are taking place and the area over which anodic reactions are taking place. So, this situation can arise, and this the example to this particular phenomena, particular instance is also available. For example, if we consider galvanic coupling of let us say we consider galvanic coupling of copper and steel and this steel means plain carbon steel in sea water. Now, if you go back and look at some of the lectures in corrosion 1, you will see that when cathodic, let us say this is copper and this is steel I consider to be Fe. So, if they are having similar area, then the corrosion of anodic component, which is nothing but the iron is the anodic part and copper is cathodic part. That time, of course, the anodic part would corrode and cathodic part would get protected, because the cathodic reaction, and in this case the cathodic reaction is O2 plus H2O plus 4E equal to 4 OH minus. This is the cathodic reaction that happens on that copper surface. Galvanic series, if you see in the sea water, copper is situating on top of iron, that is what copper would act as cathode, and the current will flow from copper to iron in the conductor. But if we consider electrolyte, the current will flow from iron to copper in the electrolyte, and the anodic part, the anodic reaction would be, this will be the anodic reaction. So, if they have similar area, the anode would corrode, but the corrosion rate would be not that significant. But if we have a situation where copper area is large and iron area is small, that time we come across a serious corrosion of iron. this part would corrode at a very fast rate. So, in this case iron dissolution rate, so we call it corrosion rate, would increase seriously. The reason is, since we have a very large cathode area, this is the cathode area, and this is the small part is anode area. Very large number of cathodic reaction would happen on copper surface, and in order to supply electrons for those cathodic reactions. So, this cathodic reaction, in order to supply those 4 electron per oxygen molecule reduction, iron has to dissolve. Now, if there are 100 reactions over the area of A, cathode area, so this 100 reaction needs 4 into 100 electrons, and this of course cathodic reactions, oxygen reduction in neutral solution. So, these many electrons need to be supplied by the smaller anodic area. So, this 400 electron to be supplied by smaller iron area. So, that means had it been equal area, so the 100 reactions is happening over area of let us say 10 centimeter square on the copper surface, the same 100 reactions are taking place, 100 not 100. So, it will be 200, because for the iron oxidation we need 2 electron to be taken out. So, that means 200 reaction need to take place on the 10 centimeter square iron surface. But in this case, if this is 100 centimeter square and this is 10 centimeter square, so then if I consider 2 electrons which are taken out from iron, then 200 reactions per 10 centimeter square need to take place on iron surface, and here it is 100 reactions per 100 centimeter square. So, we could see that in the beginning we had 100 reaction per let us say 10 centimeter square, sorry. So, if we consider equivalent reaction over this 10 centimeter square of the cathodic area, so the equivalent area amount would be 10. So, that means here it is coming 1 reaction per centimeter square. So, it would lead to 10 reactions per. So, now if I consider in the beginning let us say equivalent area, equal area. So, this is copper, this is iron, and 10 centimeter square for copper and 10 centimeter square for iron, then the number of reaction on copper would be 10 divided by 10 centimeter. So, 10 reactions per 10 centimeter square area, and similarly for iron it will be 20 reactions part 10 centimeter square area, because when it is 10 reactions per centimeter square. So, that means we need 10 into 4 electrons. So, which will be given by 20 reactions into 2 equal to 40. So, this becomes 40, this becomes 40. So, the 40 electrons from iron surface, because iron we are taking out 2 electrons. So, that means here 20 reactions per 10 centimeter square. Now, when the area of the copper surface has increased 10 times, which is 100 centimeter square, now we are having 100 reactions, because those reaction is statistically distributed. So, now see this 400. So, that means 100 reactions means we need to have 400 electrons, and this 400 electrons to be supplied by the smaller iron area, which is 10 centimeter square. So, that means 200 reactions by 10 centimeter square. So, we could see that this amount and this amount, if we compare, so that means here we have 2 reactions per centimeter square, and here it is 20 reactions per centimeter square. So, that means for iron, if we compare in those 2 situations, this case we have larger electrons, larger number of electrons, a greater number of electrons need to be taken out. So, the corrosion rate in this case in this case is much greater than corrosion rate. This is, let us say, case 1, this is case 2. Case 2, the corrosion rate is much higher. So, this is the situation we have understood before. Now, these particular phenomena, this particular observation, we can also explain. Let us say this is situation. So, here up to situation 4 we consider. So, this is situation 5, difference in area. We can understand this particular situation with the help of mixed potential theory. Okay. So, this is another situation. Now, while discussing this particular area factor, now though we say that the corrosion of the anodic portion when the areas of cathode and anodes are similar is not that significant, but there is a little insight to it, because when we consider, let us say we consider equal area. So, this is cathode, this is anode, AC means cathode, A means anode. Now, if you have an electrolyte around that, this is here we have electrolyte. Here we have electrolyte. That time electrolyte would have some finite resistance. This is R, resistance. So, whenever we have a resistance in a path, the current also faces obstacles. This resistance actually obstacles to the current flow. So, when we have obstacles, then of course, the current flow will be hindered, and we will not have that degree of dissolution of the anodic portion had there been no resistance. So, in one case, let us say resistance is very high. So, that case corrosion rate would be very low, because the current is having a resistance to flow. Now, if R is very small, so then of course reverse will happen, the corrosion rate will go up. The classic example is, let us say if we try to see the corrosion of any metal in a very pure water, deionized water, that case we always come across a very a low corrosion rate as compared to the situation when that water is contaminated with lot of ions, because those ions allow that resistance to drop, the solution resistance to drop, and that allows the easy current flow and the corrosion rate goes up. Now, when we consider this situation, this is the galvanic contact. Now, as we go away from this, even if the electrolyte has got a low resistance because of that contamination or presence of ions. Now, if we go away from this region, as we are going away from these regions, the resistance increases. So, that means the corrosion effect due to the galvanic coupling will be felt more near this junction point, because near that junction point the resistance offered by the electrolyte would be less as compared to the resistance offered by the electrolyte if we go away from that contact portion. So, that means if we have a situation like this, then I would have a typical corrosion process. Let us say this is anodic, this is cathodic. That case the corrosion process, the typical corrosion process would be this portion, this near to this junction, the corrosion here would be more and the corrosion pattern would look like this. So, this is the corrosion pattern. Fine, this blue shaded region is the corrosion pattern, and the cathode, of course, it is being protected because all the cathodic reactions are taking place on that surface. So, the corrosion is always more near the junction of galvanic couple. This is due to the resistance effect or the electrolyte resistance effect. Just to intimate here that because of the resistance, and if I multiply R, so this is resistance, solution resistance, and if I multiply the current, I will get voltage. So, this is also a drop we consider in that circuit. So, this is called resistance polarization. Because of the resistance of the electrolyte, I will have this voltage del V, and this del V will take the equilibrium potential to some other potential. Okay. So, that is resistance polarization. We will talk more on this resistance polarization later on, but right now we assume that the resistance offered by the electrolyte is insignificant. So, this particular situation can be there is a classical example of this situation in physical metallurgy. The evolution of structure of pearlite. So, these particular, and of course, optical metallography. So, when we will do optical metallography, we will have a typical microstructural pattern. So, it is a lamellar microstructure where these black regions are cementite and these white regions are ferrite, which is nothing but alpha, and this is Fe3C. Now, why do we get a typical appearance that the cementite becomes black and the ferrite becomes bright? that can be explained on the basis of this particular phenomenon. We will take this explanation to our next lecture. Thank you.